Good afternoon, Calc 3 gang. Hope you guys are doing well. I wanted to start chapter 13 with you, so we'll look at section 13.1. You'll notice I didn't assign any homework problems from this section. That's not because it's not important, but we'll have plenty of practice with vector fields in the other sections. So do watch this video series. It's important, the notes we're going to work through, but the homework will not come until the next section. So, all right, what is a vector field? Well, a two-dimensional vector field is a function that assigns to each point in some region of 2 space a two-dimensional vector, which we denote often by big F and then a vector symbol. So a three-dimensional vector field is a function that assigns to each point in some region of 3 space a three-dimensional vector, which we again denote by big F. So here's some examples of what these look like. So here's a two-dimensional vector field. It's just a vector, but instead of constants, you just have functions here. And however many variables there are involved, all told, that's the dimension you're working in. So here you can see this is a two-dimensional vector field, both because there's only 2 components to this vector, and then there's 2 variables. Here this is a three-dimensional vector field. There's 3 components, and you can see all 3 variables. Now don't be misled by what I just said. You might have a three-dimensional vector field where no z's show up. That's perfectly fine. It's still three-dimensional. There just happens to be no z's visible, but that doesn't mean that it somehow becomes a two-dimensional vector field. Also, three-dimensional vector fields you can think about, let's go the other way actually. Two-dimensional vector fields, I can view them as three-dimensional vector fields just by putting a 0 in the third component. So if I want to extend this to a three-dimensional vector field, I could just go comma 0, and that would do the trick. All right, so some notation. We're often going to write big F with P and Q, and then if it's three-dimensional, we'll throw in an R. And I get sick of writing comma XYZ a million times. So a lot of times I'll just write F. I won't write XYZ, and then I'll just write P, Q, and R. But when you see P, Q, and R throughout, even in future sections, it's important that we all agree that these are representing functions of either 3 or 2 variables depending on the context. So one of the first things that we want to think about is can we graph these things? Like what do they look like? So let's play around with a graph, and then we'll go from here. So let's see if we can graph this little vector field. It seems so innocent. I've written it 2 different ways. One is with the I, J, K notation. Now, this is two-dimensional, so I just have I and J components. The other is in more standard form. And so you just pick some points. Quite literally, you can sketch a graph of these just picking points. So maybe let's start with the point 0, 0. And when I plug 0 for x into x, so 0 here, and then 0 into y, I get out the vector 0, 0, which is just the point 0. So nothing really to see there. That was boring. Let's try another one. Let's plug in the point, how about we plug in 1, 1. And so when I plug that into my vector field, I get out the vector 2, 1. Now, when you see the vector 2, 1, it's tempted to say, okay, I'm going to start at the origin, and I'm going to go out 2 and then up 1. So it's tempted to graph it like that. And that's meaningful. This certainly is the vector 2, 1. But that's not going to help us visualize it, because then our vector field will just look like a sheet of paper, because you just have all these vectors so thick that you can't actually see anything. Does that make sense? Let me undo all of that scribbling. So what we're going to do is we're going to move that vector around. Keep in mind, I'm allowed to pick this vector up and move it around. Whoops. I can finally, if I'm careful, I've talked about this in class, move these vectors. So here we go. I can actually float the vector the way that I want to, and I'm going to float this vector, and I'm going to put its tail at the point 1, 1. Does that make sense? So we're going to position these at the tail. So, excuse me, I'm going to position the tail of the vector at the point that I plugged in. So I plugged in 1, 1. I got out 2, 1. So I position the vector 2, 1 where the tail of 2, 1 sits at the point 1, 1. Now, there's different ways of doing this. Some people maybe it would say, well, look, why should we put it at the tail? Let's put the center of the vector. Let's put the tip of the vector there. Again, that's all arbitrary. We're going to put the tail of our vectors at the input point. So how would you actually draw this if you couldn't literally pick up your vector and slide it? You would go to 1, 1. Let's actually erase it and do it again. And you would say, okay, the vector 2, 1 says go out 2 in the x direction, up 1 in the y direction. So I'm going to go out 2 and up 1, and then that's that vector. And you can actually see how it goes. So let's graph a couple of more just to play around with this. Maybe we could do, how about we do 1, negative 1. So this is going to go to what? Negative 2, comma 1. So I'm going to graph it and float it just because I can. I go negative 2, 1. I'm going to draw that vector, and then I can pick it up, and I want to put the tail of this at 1 on the x-axis, negative 1 on the y-axis. So right there, more or less. You could have just started here and then gone negative 2 that direction and then up 1, and you get the same thing. I'll put a big dot there to try to make that work. Okay, we could sit here and graph lots of these. Let's do maybe one more. Let's do like negative 2, 0. So this is going to go to the vector, well, y is 0, so 0, x is negative 2. So negative 2, 0 is going to go down to move 0 in the x direction, negative 2 in the y direction. It's going to look like that. So the point is, you can certainly sketch these things if you want to, and if you keep sketching them, if you sketch all of them, it's actually going to just, again, look like just all blue. There's not much to see, but you can sketch enough of them to get a sense of what's happening, which we're not going to do in this case. I'll show you a Mathematica graph of this in just a minute. So let's do another example, and then we'll see the Mathematica graph as well. So let's sketch one more of these. Here's one where it's a constant vector field. I don't care what x, y, z you plug in, you always get out j. You could write this as 0, 1, 0. So if I want to plug in this point, I'm going to go 1 in the y direction. So let's label x, y, z. I'm going to go 1 in the y direction. It's going to look like that. If I plug in this point, I go 1 in the y direction, 1 in the y direction, 1 in the y direction. If I plug in this point, I go 1 in the y direction, 1 in the y direction, 1 in the y direction. Wherever you are, you just go 1 in the y direction. And so you can imagine all of these arrows flying at you. It's kind of scary, actually. So that's that. So a couple of comments. Graphing software tends to scale the vectors. The relative sizes are correct, but the actual lengths are not. Notice that here, all these vectors have length 1, and they're all pointing in the same direction. And so if you graph this on Mathematica, they might appear really small, scaled, but the relative lengths are not. If we scroll back up to this one, I guess I should have done one more example here because the lengths all look the same. Maybe we could plug in, let's plug in like the point 4, 0, and we're going to get out what the vector 0, 4. So I'm going to go over here to 1, 2, 3, 4 on the x-axis, and I'm going to go up to 4. And so that one you can see is longer. So these vector fields, when you're graphing them, you're getting vectors in different directions and with different lengths. Potentially, here's a case when everything is constant. So as we were saying, graphing software tends to scale the vectors, so don't trust the lengths. Mathematica, you can plot vector fields in Mathematica. It actually centers each vectors on its input point rather than placing it at the tail like we do. It doesn't matter. This is actually the Mathematica plot of example number 1. So we should write that down so that you know this in your notes. So this is the Mathematica plot of example number 1. And then I'll just mention the input code. If you ever want to do this, you can do vector plot, or if you want to go 3D, you would go vector plot 3D, and you can look up the how you would actually get the syntax right. But those are the functions that you can plot these in Mathematica. You don't have access to Mathematica right now. I know that, not a big deal, but you might at some point. So let's end this video here, and then we'll continue with some examples in just a moment.